This presentation shows how LUSAS can be used to analyse the consolidation of an earth embankment constructed on clayey soil. We're modelling a 2D slice of what will be a long uniform earthen structure. The cross-section of the embankment is drawn simply using surfaces. In fact, we're using a half model since it's symmetric, and it's meshed with plane strain elements. A 6 metre depth of existing soil is included in the model, 3 metres of peat overlying 3 metres of clay. The embankment is constructed in 2 stages with a delay between to allow for the consolidation which occurs due to the changes in pore water pressure in the soil layers below. Later in this video we'll look at how the consolidation is modified by the introduction of sand columns ahead of the construction of the embankment. But for now, here's the model, and we're looking at the undisturbed soil on site, and specifically the contours show the initial pore pressures. The water table is at ground level, so the hydrostatic pressure is 0 at ground level and increases with depth to 60 kilopascals at the lower edge of the clay layer. The first 2 metres of the earth embankment is installed over 2 days, and if we set active the time step at 2 days, we see the embankment appear, although we're only looking at the contours in the soil below, because it's the pore pressure below that interests us. And we can see the excess pore water pressure under the weight of the embankment increases to over 80, nearly 90 in fact, in the clay under the embankment. There's a pause in the construction to allow the pore pressure to dissipate, and in this example we've waited 200 days, and if we set this time step active, we can see that the pore water is pretty much back to the hydrostatic case. Then the second and final 2 metres of the embankment is installed on top, and we see a very similar situation repeating. The final time step of this analysis is 1,000 days, so that's more than 2 years after the embankment was constructed, and so, as we'd expect, the pore water is back to the hydrostatic case. Now, let's consider the difference if we install sand columns in the soil on site, and then construct the embankment in the same 2 2-metre stages. Now, when we look at the pore water pressure below the embankment at 2 days, the contours are quite different, with the sand columns providing effective drainage for the clay either side, the higher values of pore pressure existing in the clay parts. At 200 days, of course, we see the pressures back to hydrostatic, and a similar pattern is seen when the final 2 metres of embankment is installed, the immediate effects, and hydrostatic 1,000 days later. But what's important is how quickly the pore water pressures dissipate, or perhaps even more important, the displacement, the settlement that the embankment experiences and the period over which it occurs. And that's probably best seen in this graph, which can be readily generated using the LUSAS graph wizard. Here, the green line shows us the original displacement versus time. The red line shows us the same for the second analysis, the one with sand columns. The first most obvious thing we see is that the magnitude of the long-term settlement indicated by the green line reaches about 480 millimetres, whereas the red line doesn't exceed 200, considerable reduction. This is, of course, often the primary purpose of stone or sand columns, to improve the load-bearing capacity and reduce the settlement in soft, compressible soils like clay, primarily by effectively increasing the soil stiffness with these vertical inclusions. That's why they're called columns. Secondly, we can see in the green line that the displacement takes place over a much longer period. When the second stage of the embankment was installed at 200 days, it doesn't look as if the first stage had fully completed its settlement, and likewise the final settlement isn't reached until something near 700 days, about 2 years. On the contrary, the red line shows us that the first stage settlement was practically complete within about 50 days, and likewise for the second stage. Hence, the stages could be moved closer together, and the whole process happily completed in a much shorter time frame. Of course, the effectiveness of sand columns in reducing settlements and settlement periods are very much dependent upon factors such as the column spacing, the diameters, and the properties of the surrounding clay soil.